In this video, we will show a practical example of a motion simulation using parametric equations to check whether a mathematical solution of a solar gearbox system is correct. In other words, whether the rotation of the gears and their teeth fit together perfectly during the movement. In this way, we can visually test whether the physical model or prototype can be built. See the final graphical model. During the simulation, the list of variables is also shown on the graphic screen. The central gear, called the first stage sun gear, rotates and moves the planetary gears around it. These gears transfer the movement to the annular gear in the second stage, causing the modification of torque, speed, and direction of rotation. This system is used in several mechanical devices. In this example, we will show the technique that engineer Norberto Mazzo, a renowned expert in this area, uses to graphically test a gear calculation before designing a physical prototype. To calculate each tooth of the planetary system, he uses an application developed by him and called ProGear, which calculates the graphic contour or sequence of points of the gear tooth contour according to the speed, torque, reduction, etc. conditions of the planetary system. This sequence of tooth points is imported into SolidFace using a very simple import function called CADIN import file. Let's look at the CADIN import format. See the example in CADIN format to import a straight line. A straight line with a x and y coordinates starting point at 1010 and an ending point at 5050, dashed with an average thickness of 2. Note that the first value, 351, is the number of the command to import a straight line. Returning to our simulation, let's show in a simplified way how this simulation was created. First, import the gear teeth and rotation circles using the SolidFace CADIN format. The teeth contour, center lines, and rotation circles of the gears are generated. Note that the outline of the teeth is made up of small straight line segments. The next step is to create the full gear profile. To create the gear, we could select the tooth using a selection area, and then use the pattern rotation command to create the gear. However, since we are going to simulate movement, a selection by area is not appropriate. At a given moment of the movement, the fixed selection area will not contain the straight line segments of the desired tooth during the simulation. To solve the problem of rectangular area selection, it's safer to select the tooth using the contour selection option. Activating the contour function. The type is open contour plus the selection option. Then, identify the segment contour first line and contour end line. The first line endpoint shows the contour direction. Now activate the rotation pattern function to generate all the teeth to create the sun gear of stage 1. Sorry, I made a mistake. It is not 4 teeth. Let's edit the last command in the list. Double-click on its position in the command list. This gear has 9 teeth. Therefore, the rotation angle of each tooth is equal to 360 degrees divided by 9 teeth. Do the same procedure to create all gears. See the result. Create the stages 1 and 2 texts. Type Enter to repeat the last command. Our goal is not to provide a course on calculating gears in planetary systems. For that, we would need several hours to detail all the process steps. We will show you in a simplified way how to develop a parametric model to create a simulation. Let's show the already defined list of variables in chronological order of creation. When you edit a variable, listing the variables in chronological order is very important. A variable used in the expression must be defined chronologically before the variable being edited. Initially, a variable named u and a variable named ang were created, and then was defined a variable angs1 as equal to variable ang. The rotation angle of the sun gear of stage 1, that is, the input gear, is controlled by the variable angs1, which is equal to the variable ang. Let's change the variable ang to a value equal to 10. To check all gears' position at this angle, click on the desired variable in the list of variables and edit it to 10. The variable angs1 was changed to 10, and all the equations associated with it are also modified. The gear positions were modified according to this angle. Let's show how to create a parametric text list of variables on the graphic screen. The first line of text is about the rotation angle of the sun gear of stage 1. Its rotation is controlled by variable angs, one that is equal to ang. The second column indicates the variable name and its expression. The prefix character hashtag indicates that the content of this variable can be shown. The suffix g indicates that the degree symbol will be shown. Let's align with the first text column using an info par xy function. For x coordinate, indicate a position on the graphic screen, and for y coordinate, indicate it with the help of the info point text or dimension function, clicking on the first text. You can choose to show the parametric expression instead of its value. Next, create all the texts for the movement variables. The motion simulation will have the step controlled by the ang variable, which is the first created variable. Click on the simulation button. Its initial value is 0. Its end value is equal to 360, and a step increment of 2. The variable list should be shown during the movement, also with an automatic loop and reverse direction. In other words, the sun 1 gear rotates from 0 to 360 degrees. To create the simulation, you need to associate a rotation command to each planetary box gear according to the desired variable or parametric equation. These rotation commands are already created. I will create it as an example of how you add a rotation function to a gear. Let's first select the gear with the closed contour function. Let's click on any line of the gear. Then create and associate a rotation command with the angle of the angs1 variable. See the command Save in the list. We are going to delete it because all rotation commands are already created. Do the same procedures for all stage 1 and 2 gears. See that all rotation commands are already saved in the list. For instance, for the sun gear of stage 2, the rotation angle is equal to the variable angs2. For the auxiliary planet gear was used the variable ang_t1. Note the movement command is saved at the end of the list. Let's show the simulation. Abort the simulation and start again, but now showing the variable content. Now we are going to create 2 new auxiliary planetary gears of stage 1. First select its contour. Creating a total of 3 gears. The angle will be 360 degrees divided by 3 and a total of 3. And do the same for stage 2, but now with a total of 4 gears. And the result is Up to this point, we have shown how to create a simulation of a mechanism. Let's create some dimensions and check how they behave visually during the simulation. First, change the ang to 10. Let's indicate the angle from the center of this gear to the horizontal center line, creating an angular dimension. Now create a dimension that measures the horizontal distance to the vertical axis. Running the simulation. Don't forget to move the simulation to the end of the list. See the result. Now let's imagine we want that these two pieces of information, the angle and the distance, created during the simulation be captured by variables ang1 and dist1. Let's activate the parametric association function to an angle. To do this, associate a variable with an angle and another variable with the distance. Choose the function associate variable with an angle. Inform the variable ang1. The variable does not exist. Confirm that you want to create it. It is shown in the variable list. Identify the center points of the gear and the center of the planetary box. And also activate the parametric association to a distance. Identify the center point of the gear and any x-coordinate point, and measure the value horizontally. The variable are yet equal to 0. Let's check the current value of these variables. Process parametrically the active group. Note that two variables were modified according to the condition that ang1 is equal to 10. The second part of this video will show an example of how we can extract real-time information from a motion simulation to interact with the process to modify it, check for collisions, or study the viability of a mechanism.